Start our last speaker today is John Imbrie from University of Virginia. The title is Level Spacing for Non-Monotone Anderson Model.
Okay, well, yeah, thanks for slotting me in here, giving me the opportunity to talk about a result that just hot off the presses, just posted last night on the archive. It's 1506, 06692. This is with Rajinder Mavi, who's been a postdoc with me at the University of Virginia for the last 3 years, and I guess he's going to be working with Jeff next year at MSU. One thing I think it was clear from the talks earlier today from Abel and Elgart's talk was that level spacings are good. All right, lots of good things happen when you know that the eigenvalues of some quantum Hamiltonian, especially in the context of disordered quantum systems or random matrix theory, you'd like them to be spaced out. That's certainly a key ingredient for many sorts of results that you might want to work on, such as localization, issues of even, say you want to prove something about the AC conductivity, and the limit as the frequency goes to 0, well, you need to know something about hopping amongst these levels. You need them to be separated. So there are going to be 3 main ideas in this talk, and I'm not sure I'm going to get to the third idea, but let me just list them here. First of all, there's a new proof of a minimum level spacing condition. So replacing the Minami proof, which has been a staple of study of disordered quantum systems for many years. In the context of Bloch-Anderson models, which I'll define carefully. In these Bloch-Anderson models, there's the Minami estimate is not available. All right. The second thing same main idea I want to talk about is the method, which should be of interest in its own right. If the method is going to involve iterated Schur complement, in rough form, what we're interested in focusing on a particular energy level, or the neighborhood of a particular energy level in the system. We're going to define some window about that energy, and an associated Schur complement decomposition of the Hamiltonian will take the Hilbert space and break it up into sort of a resonant Hilbert space corresponding to modes that are closely aligned with E, and a non-resonant, which is sort of easy to deal with and get rid of. Now, a single step like this will reduce the dimension of the Hilbert space dramatically. But what we do is actually continue to repeat this process, narrowing that energy window down lower and lower. So we get a sequence of Schur complements. And the dimension of the Hilbert space just keeps on going down and down and down. And eventually, it's basically only one state left in the Hilbert space. So it's very intuitively clear picture of what's going on, and so I think it'll be provides a great deal of precision in the ability to fine-tune exactly what you're looking at in energy space and position space. So it has potential for applications for many other problems than the one that I'm discussing today. And the third idea here which again I may not get to, but at least I'll put it out here, and if I don't get to it, please, I encourage you to have a look at that paper. It's something that I call the energy following procedure. What this is about is there's sort of an issue of like even finding the eigenvalues, right? I'll get to this in more detail, but there's sort of a crude method. If you want to know, let's say there's a minimum level spacing condition, you could divide the spectrum. Let's say you have bounded spectrum of the Hamiltonian. You could divide the spectrum into a bunch of small intervals and ask the question, are there two eigenvalues in any one of these intervals? And if you can show that with a high probability none of these intervals have two eigenvalues, then you have a minimum level spacing condition. However, that presumes that the probabilities of having two eigenvalues in an interval decay are smaller than 1 over the length of the interval, so that you can actually sum the number of intervals. If you can't do that, which is the situation that I'm working with here, you just can't do this crude summation technique. You have to actually say, well, okay, let's look at each individual eigenvalue. Does it have a window about it which is free of other eigenvalues? And if you can do that, just focus on the actual eigenvalues. You have to follow them through a process of approximation from so to speak, the original eigenvalues, bare eigenvalues, which are just the potentials at the individual sites. So anyway, I'll get to that in more detail, hopefully later. But anyway, just to make a little connection with the talks this morning, there's this whole notion of labeling, which is connected to this idea of energy following procedure, which this morning the two talks had a very nice one-to-one mapping between the size of the lattice and the eigenfunctions and the eigenvalues. So here this is not a one-to-one mapping, so it's actually a one-to-many, which every site then is going to have many eigenvalues associated. There's a lot of overcounting in my procedure. But the bottom line is that this overcounting is somehow under control. So that when you actually try to sum over all the eigenvalues, it doesn't matter if you overcount. You can still get the results on level spacing or localization that you're interested in. Nevertheless, it might be nice to try to use some of those ideas in this morning's talks to try to tighten this procedure up and make it look a little nicer. Okay, so let me just talk a little bit about some background of this problem. One thing is, you may be wondering, why is it that we all of a sudden having all these new approaches to localization, which of course has been it's a well-established field for something like 30 years. Why all of a sudden all this interest, especially in eigenfunction approaches, trying to avoid use of Green's functions. This goes back to a work that I put out about a year ago, where I proved exponential decay of this eigenfunction correlator in the Anderson model, like this. So if you sum over the eigenfunctions, psi alpha of x, psi alpha of y with absolute values, take the expectation, you would like this to be exponentially decaying. This is something which went through the fractional moment method, but hadn't been obtained with multiscale analysis. So this paper here provided a multiscale analysis proof, which was basically motivated by the idea of developing a tool for many-body localization. In fact, this is underlying many, not just that work, but also the work I'm talking about today. And also, I think Abel and Elgart mentioned their motivation as well of trying to avoid relying on the Green's functions, which have seemed to be rather difficult to formulate in the context of many-body systems. Another important issue, so that's one, is the many-body applications, which, of course, remain to be done, but we have to start somewhere. The second issue has to do with less singularity. If you look at something like this, of course, the eigenfunctions on a lattice are bounded by 1, so there's no poles or anything like you have for the resolvent. And so that's, the singularities are always, you have to deal with them by backing off from the places where the singularities occur. And that typically forces you to go to stretched exponential as opposed to exponential decay. So that's the second motivation. Finally, and this goes back to my very first comment at the start of the talk, which is the idea of level spacing is good. In fact, I was, there's this paper on many-body localization, which basically says assume a level spacing condition, a minimum level spacing condition, then you have many-body localization. So that places, obviously, a high priority on understanding new ways of controlling level spacing. And that was also a motivation for Virginia and I undertaking this project. Okay, so let me just mention a little more background here. The Minami estimate is the traditional approach to issues of level spacing. And it would look something like this: probability of 2 eigenvalues in some interval, let's say E minus delta, E plus delta. And typically the Minami estimate will look like this. For some alpha. Maybe that might depend upon the exact form of the potential probability distribution. And many things, good things fall from this, Poisson statistics, AC conductivity, things like that. But as far as the level spacing condition, the answer is yes, if alpha is bigger than 1/2. This is the condition which came into Abel's talk as well. And I guess this was basically the content of the idea behind Germanet-Klein, which was that if you want to control the probability that the min of E alpha minus E beta is less than delta, what you can do is make a sum over energies of this bound, delta to the alpha lambda squared. And let's say we have a bounded spectrum between, 0 and 1 or something like that. The number of terms in this sum are going to be of order 1 over delta. And then we have delta to 2 alpha lambda squared. And this is going to go to 0 for small delta, provided alpha is bigger than 1/2. Okay, so you have a minimum level spacing condition, at least as long as you have Minami and you've got an alpha bigger than 1/2. But what do you do if there's no Minami or alpha is less than or equal to 1/2? Well, that's the subject of today's talk. There really isn't too many alternatives to the Menominee approach out there.
So you're summing over the energies inside this interval, right?
Summing over, let's say, take a lattice of energies separated by delta.
Yeah, but well, usually, I mean, if you take a fixed size interval, the number of energies in there is proportional to the volume, right? So I wonder whether the volume factor has disappeared in your sum.
Well, the volume occurs over here.
No, but
This whole thing
I
is
thought
really,
you were summing. Wait,
the volume is really not relevant for this discussion, because what counts is that the thing has to tend to 0 as delta goes to 0. All right. Okay, so that's. So now let me go over to the actual model that I'm going to talk about. So this model is, you might call Spencer's laboratory problem. He kept posing it to many, all kinds of people, and finally some people started to get cracking on it. And so let's take a single-site block Hamiltonian, which looks like this. And then we take an H0 by just taking the sum over x and lambda of hx. And then we need some hopping. The exact form isn't that important. Let's just take v is some small number times j, times of the identity matrix in this 2 by 2 spaces. So gamma small, and j is 1 or 0. All right, and then finally you take h equals h0 plus v. So this is called might be called a random block Hamiltonian, or a block-Anderson model, I guess you know. In other words, it's just like the ordinary Anderson model, except at every site, instead of having a one-dimensional space, you have a two-dimensional space. Now, the important things about this is this non-monotonicity. But as the parameter varies, this u, of course, is going to be the random variable. Ux are going to be IID, smooth random variables. And for the Wegner estimate, typically you need the energies to move up together in concert, so that you can be sure that any energy moves through an interval in question. Here, one goes up and the other one goes down, and the Wegner estimate is out the window, at least the standard proof of the Wegner estimate. Now, I should say that there's been quite a bit of study on block Anderson models and related alloy Anderson models. I mean, at least a dozen, maybe 24 papers on these things. So there's, in terms of people have managed to get around these issues to establish localization and so forth. I will point out one paper, or actually two papers of particular interest here. Elgart, Seamus, and Soden, they used a fractional moment method And they attain bounds on the integrated density of states. And and as well in exponential localization. So essentially they obtain this bound here. For the Spencer model. Then there's another paper of particular interest, Elgard and Schmidt, I think it was in 13, where they have n-level Manami. And it wasn't quite this model, but I don't think they could quite handle that model, but they could do a very closely related model. Where the blocks look like that. But they needed some randomness off diagonal as well. Okay, but whether, the precise details is not that important. I'm just trying to focus on, I want to make sure that I credit where credit is due. This paper definitely does have results on block Manami type estimates. Manami type estimates for block Anderson models. Just not quite this particular one. But mainly my focus in this is developing a new method that can be used very widely applicable. By the way, the form of this model is very suggestive of the many-body problem, even though it's obviously a one-body problem. Because what we have here is this H naught. Is really a direct sum of spin 1/2 spaces, whereas but if I replace that with a tensor product, then you have a many-body system. Okay. Laughter in the audience. Okay, but that's permitted. I'm supposed to have a few jokes here, but anyway. All right, so let me give you a crude picture of where the level spacing method comes from. Just sort of back of the envelope calculation. First of all, let me just talk about density of states. And then I'll talk about level spacing. If we have one site, the two energy branches for that Hx look like this. We have lambda 1 is the square root of 1 plus ux squared, and lambda 2 is minus that. Now you'll notice that there's a quadratic minimum here. So if you were to ask the question, what's the probability that lambda is in one of these intervals, e minus delta, e plus delta, this would go like delta to the 1/2. Okay, well that's a single site. What if I had n sites? By the way, one way to see this, I mean it's obvious from the picture, but one way to see this is if you look at the determinant of hx minus e, this is a quadratic polynomial. And so the probability that this is smaller than anything goes like the square root at worst. If you have n sites, then determinant of h minus e is a polynomial of degree 2n. in the U's. Therefore, the probability is going like delta to the 1 over 2n. So obviously this is a much weaker bound than we're used to dealing with, at least in the traditional Anderson model, but it's actually quite workable. And this can actually replace the usual Wegner. Wegman is the grocery store. Yeah. Something happened to me a lot in Princeton because there's a very nice Wegner's there in a nearby shopping center. But anyway, this idea really was initiated by Bourgain, 2009, where he looked at the so-called Froelich model, and he used a Cartan lemma. Here the Hamiltonian was actually an analytic function of the random variables, and he used the Cartan lemma, but that's basically a kind of polynomial approximation. And then he was able to prove localization for that problem, which had eluded other efforts. Kruger has also used Cartan lemma method. So so the idea has been out there for a little while. Let me continue with the crude analysis here. To try to make this a little more quantitative, which really wasn't put out that explicitly in those papers. If you have n sites resonant with E, let's say within epsilon, epsilon typically I'm going to take to be gamma to some small power like a quarter. So epsilon is going to be a small number. The probability of that is something like epsilon to the n. So overall, the probability of a block size n resonant with E to within delta is going like epsilon to the n times delta to the 1 over 2n. Or you could take the smaller of either of those two. It doesn't much matter. And so you can write this as an exponential. So it's e to the minus n log epsilon minus 1 over 2n log delta. And then you can say, well, what's the worst case as a function of n? And the worst case turns out to be n is basically square root of log delta over log epsilon. And so this is going like e to the minus square root of log delta square root of log epsilon. Now you have to remember that epsilon is a small number. Delta is also small, but the whole idea here is to understand what happens as delta goes to 0. So delta is the number which is going to 0. So what we find here is that we get e to the minus square root of log delta as the behavior of this probability as delta goes to 0. It's not quite what you might have hoped for compared to the Menominee estimates that I wrote down as a model earlier, which involved things going to 0 as a power, or a typical Wegner estimate. Nevertheless, this you can think of this, the glass is half empty or it's half full. At least we've got something that's actually good enough to prove localization and so forth. And maybe it's not the true behavior, but it's better than nothing. One thing it does, so it's not wholly continuous density of states, integrated density of states, but it's better than log Hölder to any power. All right, let's talk about the corresponding analysis for level spacing. For level spacing, instead of a determinant, we want to use the discriminant. So what is the discriminant? For any matrix M, it's a product of the eigenvalues, the differences of the eigenvalues squared. And this is actually a homogeneous polynomial in the entries of M. And the degree is rather high, is 2n times 2n minus 1 if M is a 2n by 2n matrix. So basically 4n squared. So if you want to look at the probability of the square root of the discriminant, obviously this is relevant for the level spacing condition. If two eigenvalues are going to get close, then that discriminant is going to get small. So if we look at the probability that the discriminant is less than delta, again we have this epsilon to the n because we have the probability that n of these sites are somehow in play should be going to 0 with n. And then we have delta to the 1 over n, 2n squared. Coming from the fact this is squared, we took the square root, so that's, instead of 4n squared, it's 2n squared. Yeah?
That kind of heuristic somehow suggests that if epsilon is equal to 0, you wouldn't have degenerate eigenvalues, right? But I would expect that if epsilon is equal to 0, so in other words, when you have no random potential, you do have degeneracies, right? So why the things improves as epsilon goes to 0?
Well, you see, I'm not taking epsilon to 0. I mean, you see, epsilon is supposed to represent a probability, right? If there's no randomness.
Wasn't epsilon something like coupling constant in power 1/4 or something like that?
What is epsilon? What is epsilon for you? That may be that.
Epsilon is gamma to the 1/4.
model. When you define the model, what was epsilon?
Epsilon is
Exactly, it's that.
No, it's not. And what was gamma in the original model?
Gamma was the coefficient of the hopping.
Oh, yeah.
Okay.
So you're not looking at the case when epsilon is small. I saw that this kind of balance that you have written is based on the situation when epsilon is small. Otherwise, it works against you, right?
Well, I think, let's see, so if epsilon were really, really tiny, then the probability that any particular site would be within epsilon, would have an energy within epsilon of E, is correspondingly tiny.
Well, let's take a case epsilon equal to 0, right?
Yeah.
Then we just have Laplacian. Laplacian might have degeneracy, right?
No, if epsilon equals to 0, you just have product of independent blocks.
You might have function which looks like a wave in one direction. You can have a wave function in the perpendicular direction in two dimensions. You have a lot of degeneracy.
No, but it was the coupling of the hopping, not the coupling of the...
No, but the coupling is in front of the random potential,
So
right?
it's in front of the hopping.
No, it's in front of the hopping.
So it's stronger.
It was a very unusual choice of
But it's,
zero and
it's the same convention as in Europe.
I see, okay.
Yeah.
That's bad notation. Don't call V. You call in the paper. You call V the.
kinetic energy.
Oh,
V is the kinetic energy.
Don't do that.
That's capital V. Okay, but anyway. Little v is a potential, capital V. Anyway, okay, so anyway, this is just a back of the envelope calculation. Anyway, you can see I'm going to reproduce what I did over there for the Wegener estimate. Now for the level spacing estimate, you see this is going to be, when we cut to the chase, it's going to be e to the minus log delta to the 1/3, and then log epsilon to the 2/3. Okay, so despite the fact that the degree of the polynomial is markedly larger, we did lose a little bit. Instead of a 1/2 over there, we got a 1/3, but it's still going to go to 0 reasonably rapidly as delta goes to 0, just not Holder continuous. All right, so now let me state the actual theorem that we were able to prove. So for gamma sufficiently small, there exists some b bigger than 0 such that the probability that the min over alpha different from beta, E alpha minus E beta, those are the eigenvalues of H, is less than delta, less than or equal to lambda, e to the minus b, log delta, and now instead of 1/3, we have 1/4, and then we have log epsilon to the 3/4. So we had to back off a little bit from this back of the envelope calculation, but it's a similar form of dependence. And this is for any lambda and any delta that is moderately small. Some gamma 1/4 over 4. Okay. So like I said, glass is half empty or it's half full. If you are looking for a result similar to what you're used to from a NAMI estimate, you'll be disappointed. But if you're happy just to have any sort of estimate, like I am, you'll be pleased. Is this the true behavior? I don't believe it is the true behavior. However, I think that if you want to do better, at least in a general context, you're going to have to exploit the smoothing of the density of states that you expect from the hopping terms in the Hamiltonian, which have always been problematical. It's been always difficult in this field to exploit those terms as a way of smoothing out the density of states and other issues. So unless you want to proceed along those lines, this may be close to the optimal result. Yeah, that's an important point. You see, another thing that's different from this traditional Menominee estimate. The way I like to think about it is the Menominee estimate normally is dominated by basically the square of the density of states, right? So you have probably two eigenvalues in an interval. The first term, so to speak, the leading contribution in an asymptotic expansion in lambda would be the term, the independent term that there is one eigenvalue in the interval squared. However, there is a second term in an asymptotic expansion in lambda, which is proportional to lambda, which corresponds to, so to speak, a resonant situation where there's some kind of resonant region here, and translates to this region, or then we'll just give one factor of lambda. But this particular region happens to have two eigenvalues in this quasi-mode Hamiltonian, whatever that means, which are closer than delta. Now, as it happens, this term is much larger than the traditional Monami term. And so it was not necessary to write the traditional Monami term. But both actually occur in the proof.
What conditions do you need on the randomness again for that result? How smooth does it have to be?
Well, I didn't probe into that direction. I just took that it was, actually I just took a uniform distribution on -1, 1. But yeah, presumably you could do a Holder estimate, and it might change some of the constants there. That's about all. So somehow, heuristically, what you have here is a situation where you have a level, you have a kind of a conditional density of states. Given that there's an eigenvalue here, how likely is it to have another one nearby? That's kind of what we're asking. It's very difficult to work directly with a conditional probability like that, but that's why we have to go with this complicated energy following procedure to actually construct the eigenvalue that we're going to work at, and then look about what's going on in the spectral neighborhood of it. Okay, so let me, before time gets too late, let me talk about the implementation of this idea using the repeated Schur complement. Okay, so we're going to do basically multiscale analysis via repeated Schur complement. So there's this thing I'm calling the fundamental lemma, with apologies to our friends in number theory. Let K be a matrix in block form. To say it's a symmetric matrix. And we're going to assume D minus E inverse is bounded by epsilon inverse. And B and C are small. They're bounded by gamma. And both epsilon and gamma over epsilon are small. And furthermore, let's take lambda minus E. We're going to look at a neighborhood of some fixed energy of width epsilon over 2. Then, the basic fact about Schur complement is that f lambda phi equals lambda phi. You have an eigenvalue of the Schur complement. Well, I guess I should have said what the Schur complement is. Then, if you have an eigenvector for f lambda with eigenvalue lambda, then K on this thing in block form, this produces an eigenvalue of the original matrix K. So in some sense, when you reduce the Hilbert space to the upper left block, you have an effective Hamiltonian. Now, the unfortunate fact about this Schur complement formula is that there's a dependence on the energy here, the fact of light.
No, but not for this
No,
equation. Then it would be
It's
x
on
lambda
zero,
by 0.
yeah,
Yeah, I tweaked it a little bit just to, it was convenient for most of the constructions in the paper. This is basically an effective Hamiltonian. Unfortunately, there's a weak dependence on lambda, which is an annoyance, but it's not fundamentally a problem because it is a very weak dependence. If you look at the derivative of this thing with respect to lambda, or take a difference, you see this is of order gamma, this is of order gamma, this is of order 1 over epsilon. But we said that gamma over epsilon is small. If I differentiate in lambda, that gives me another 1 over epsilon, so we get gamma squared over epsilon squared. That's still small. So we have weak dependence on lambda for this effective Hamiltonian. Okay, so the spectrum of K in this interval agrees, in quotation marks, with the spectrum of F lambda. What I mean by that, if you have a bunch of eigenvalues of K, then there's a bunch of tilde eigenvalues of Fe, and lambda I minus lambda I tilde is less than or equal to 2 gamma over epsilon squared lambda I minus E. All right, so if we didn't have dependence on lambda, then maybe these eigenvalues would perfectly agree. They don't perfectly agree, but their difference is really a small number times the distance away from the reference energy E. So what does this mean? This means that if E happens to be either one of the eigenvalues or very close to one of the eigenvalues, and if Fe has a minimum level spacing, let's say of order epsilon, then that implies that K also has a minimum spacing around E of order epsilon. The two sets of eigenvalues are close enough in the vicinity of E that a gap in one set translates into a gap in the other. And that's the basic method that we use to treat this issue of minimum level spacing. So just let me note there's an important estimate which I referred to above, but let me just state this precisely. That you have a kind of Lipschitz continuity in the norm of these operators as a function of the Schur complement parameter with a small Lipschitz constant. And this is something which is used to seek out the approximate eigenvalues in this energy following procedure. Okay, so I've told you this basic lemma, but I didn't tell you how to make this block decomposition.
John, what is Fe? Lambda you have up there, but Fe?
Yeah, that's just where lambda happens to be equal to E. So we have E as a reference energy, and we sort of we make some kind of construction or bounds to determine how likely it is that Fe has this level spacing or is resonant or something like that. And then, but that automatically says something about all the F lambdas in the vicinity of E because of this Lipschitz continuity. Okay, so we need to talk about the block decomposition. of the Hilbert space. We're going to fix E. We say that X is resonant if the distance from the spectrum of Hx to E is less than or equal to epsilon, which is gamma to the 1/4. So the probability is of order squared of epsilon, as I indicated earlier. If you want to draw a picture of what's going on, we have basically a dilute set of sites. So it's kind of a percolation problem. There's a certain probability that a site is in the resonant set. Of course, in site percolation, you know, you can have an extended block, right? You could have an X and a Y living in the same block, but the probability that they lie in the same block would decay like the epsilon to the distance between X and Y. All right, so this then defines this set of sites defines the first resonant set. And the corresponding indices determine A. In other words, A is a restriction of the original Hamiltonian to the resonant sites. And correspondingly, D is a restriction of the original Hamiltonian to the non-resonant sites. And B and Z are the hopping matrices, which hop between the resonant sites and the non-resonant sites. So, okay, so I better, I haven't been red flagged yet, but I know it's coming pretty soon, so let me try to wrap things up a little bit here. Let me draw that. So graphically what we've got is we can look at D minus lambda inverse as a random walk expansion. Just throw out the Neumann series for this. And of course the condition of non-resonance assures us that this is a nicely convergent expansion. So this looks like a sort of sequence of walks. If I were to look at x, y, it walks going from x to y.
D is non-resonant block.
Yes.
You put everything kind of bad in the upper block,
Yeah.
and D is kind of a good block.
Yeah. And although it's, you know, although you have a 1 over epsilon every time you, this is of order 1 over epsilon, which looks bad, but then the hopping matrices are of order gamma, and so overall it's nicely convergent. So this would be the D inverse. If you want to look at the actual B minus lambda inverse C, this would be the actual part of the effective Hamiltonian, if you will, connecting two resonant regions. This is our two resonant 1 regions. Then you've got a bunch of walks going from here to there. So you have exponential decay of matrix elements of this operator. B takes you from the resonant set to the non-resonant set, and then this propagates along, and C takes you back to the resonant set. So you get nice graphical bounds just using the random walk expansion. All right, so in step K, we're going to use, we're narrow down the windows. We're going to have epsilon k equals epsilon to lk to the psi, with psi is 2/3, and lk is 2 to the k minus 1. So we're going to have length scales growing geometrically, and these energy windows are shrinking down, going like some fractional exponential. This also governs the decay of the matrix elements. You get fractional exponential decay of matrix elements in the kth step, and likewise probabilities you have a sort of a generalized percolation problem for blocks being resonant on various scales, and you obtain fractional and exponential decay of probabilities that x and y lie in the same resonant block. The conditions which define a resonant block are a little more complicated, but you not only have to have a spectral condition, or rather, let me put it this way. In order for a block to be mild, non-resonant, the spectrum of the effective Hamiltonian, or the Schur complement matrix, has to be a certain distance away from E, namely by distance epsilon k. And so we take this matrix, Schur complement step k, with lambda, with some energy E. We have to restrict to a particular block, which means we truncate it. This has to be bigger than epsilon k. And then there's a diameter condition. And thirdly, there's a volume condition. Lk to the 2 psi over 5. So, you know, it's we're kind of a throwback, what is it, Tuesday? Throwback Tuesday back to sort of this Froelich-Spencer approach where you have resonant regions, probabilities, percolations, and so forth, which is the kind of what I've been working on the last couple of years. All right, anyway, I think my time is just about up, so let me just make one final comment, because, you know, there's these two approaches in multiscale analysis. There's sort of percolation style multiscale analysis that I've been favoring. There's the block multiscale analysis, which is what was done this morning, and they're really not that different at a fundamental level. It's more a question of style, but all in all, I would say that multiscale analysis is making a comeback and show considerable signs of legs for good results to be obtained in the future. So thank you very much.
Questions?
Yeah.
So I understood how you construct the initial resonance set or non-resonance set by comparing the, let's say, level spacing with epsilon, right? So, but presumably after you do the one Schur complementation, you then come back and do another Schur complementation, etc., right? So
Yeah.
so my question is, first of all, when you do Schur complement, you deform your operator. And it can be quite drastic in the sense that, for instance, before the off-diagonal terms were small, right? They of order gamma. But once you do the Schur complement, there is no particularly strong reason for those off-diagonal terms to be of the size gamma. They might increase quite, I can imagine, right? So.
Well, no, we keep a pretty tight control over everything.
But at least they cannot be improved, but they're not going to be smaller than gamma, right? So, but now you want to look at the new scale in terms of epsilon, so you want to look at something like epsilon k.
Well, okay, no, but think about this. Okay, that's what you just said was raises an important point. If you were to look at the matrix at nearest neighbors, yes, it would be of order gamma, but you force these blocks to separate from one another. And so the distances involved, as was obvious from this picture, the distances involved here are typically quite large, right? So that means you have many powers of gamma to get from here to there. And it's not just a matter of a usual property, it's something that you actually enforce in your construction of blocks. So blocks that are closer than LK are just combined into one block. So therefore, there's always a minimum decay length associated with any distance, which implies that well, not only graphs decay fractionally exponential in gamma, they go like gamma to the LK to the psi, or gamma to the x minus y min LK, or max LK to the psi. But the probabilities also do the same thing. They go like epsilon to the x minus y min LK to the psi. So this ensures that both the graphs and the probabilities are going to zero rapidly with k. Remember, LK is 2 to the k, basically.
But does it mean that after each step you kind of diagonalize something? Because in order to make the off-diagonal terms small, I guess some kind of diagonalization procedure is in order, right?
No, I'd use diagonalization in the other papers, but not in this one.
But what ensures that the off-diagonal terms decrease?
Because the distances involved get larger and larger.
What distance has to do with the size of the off-diagonal terms?
Well, in the random walk expansion, the longer the graph is, the more powers of gamma you have.
What I saw, you take, well, maybe we should discuss.
Yeah, okay.
Any questions? Any more questions? If not, let's thank the speaker again.